this session, we'll be looking at the three different models which are adaptive in nature, which I talked about: the moving average, the exponential smoothing, and the Holtz model. So let's first start with the moving average technique. So in a moving average, we are just going to focus on a simple rolling window of time periods, and that can be either a 2-period model or a 3-period model or a 5-period model, so on. And basically what we're trying to do is we're taking the averages for the number of periods that we selected, and we use that as a forecast for the next period. So for example, in a 3-period model, we take the first period that we have to forecast, okay, which would be time period 4, because we need to have 3 periods of data before we can actually forecast. And so whenever we're looking at averages, we refer to that as level. So then level in time period 3 will be taking the average for time period 1, time period 2, and time period 3. So A1, A2, and A3 basically represent the actual demand in each of those 3 time periods. We take the average of that. That gives us the level in time period 3, which becomes the forecast in time period 4. Okay. So likewise, if you focus on, let's say, a 4-period model, then the first period that you can forecast would be period 5, following the same logic. So here, in the setup that I gave you, right, so L again stands for level, and A is basically the actual demand, and F stands for the forecast. So it's a pretty simplistic kind of a method that is used in estimating what the demand is going to be. So let's go to the Excel calculations in this context and look at how we compare different moving average techniques and how we select the optimal value for n, which is the number of time periods to be used.
So moving average through Excel, again, I'm just taking the same data as before, 15 weeks, right? So everything shown in red is the data. So we are trying to predict the demand for period 16, right? And this is an adaptive model, as we talked about this, which means you build the model, but as new data comes in, you're going to revise the model. And we talked about taking those simple averages, right? So the level component, so I'm comparing here a 3-week and a 5-week moving average model. So the level component, let's take, for example, level in time period 3. So that's what we can start with, because for a 3-period moving model, we need data from 3 periods. We take the average of that and use that as a forecast for period 4. So I took the average for the first 3 periods, okay, which is basically 800, 1400, and 1000. Take the average. So that is going to be the level in time period 3, which becomes the forecast in time period 4. And when we go to period 4, then, right, so as the data for period 4 comes in now, so now to forecast for period 5, we take the 3 most recent periods. Okay. So level in time period 4 then, okay, will be the average of 2, 3, and 4. So as you can see, this is like a moving window, right? So we drop the first period and 4th period comes in to calculate the level in time period 4. Take the average of those 3. So 1400, 1000, and 1500. So that becomes the level in time period 4, which becomes the forecast in time period 5. So you get the idea, right? And I'm comparing it to a 5-week model. So same logic here, but to forecast in a 5-week model, you'd have data for 5 periods to start with. So you get the level in time period 5, which becomes the forecast in time period 6. So the rest of the calculations are exactly the same. And then I'm trying to see which model is better. So for that, we are going to use absolute deviation. You remember I talked about a metric called mean absolute deviation as a measure for forecast error. So here we are using the mean absolute deviation value to figure out which of these two models is better. So for example, right? So you've got absolute deviation for period 6 year. That's what I'm looking at, and that would be demand minus the forecast. Okay, so this is for the 3-week model. Demand minus the forecast, and that would be, right, we are dropping the sign because over forecasting is as bad as under forecasting. So we are getting rid of the sign, so using the absolute, right, which gives us 33.33. And then we use the same type of calculation in terms of trying to figure out what is the absolute deviation for each of these other time periods. Same logic used for the 5-week model, and I'm taking the overall average and comparing those. So whichever mean absolute deviation value is lower, okay, that's what we are using as the best approach here. So the mean absolute deviation for the 3-week model is actually less when compared to the 5-week model. So we are selecting the 3-week model as the superior approach here and using that to forecast for period 16, right? So which is basically for the 3-week case then, a level in time period 15 is 2200, which is again the average for periods 13, 14, and 15. Okay, and that becomes the forecast for period 16. So you select the best model, and based on that, right, you're trying to predict. So let's look at the plot below. Actually, it kind of tells you a little bit about what happens when you increase and decrease these number of periods, right? So the blue data, that's basically the actual data. And the 3-week model, right, is shown in purple, right? Those are the results. And the 5-week model is shown in black, right? So the thing is that as you increase the number of periods, right, the forecast is basically getting a little bit flatter here. And as you decrease the number of periods, the forecast is becoming a little bit more responsive. Okay. So let's go back to my slides and we'll talk a little bit more about those characteristics.
So based on the Excel computations, let's just try to summarize what the characteristics of this moving average technique is. So selection of the number of periods, that is a very important thing. And as we looked at it in the Excel case, we compared models with different number of periods, and we selected the periods with the lowest mean absolute deviation, right? So this mean absolute deviation, as we talked about this before, it's a measure for the forecast error, right? So it's not like a small value for n gives you better predictions. It is hard for us to decide whether it should be a small value for n or a large value for n. So it basically depends on the type of distribution that we are dealing with. So it's not like a one-size-fits-all type of a setup. So as we've gone through it, you have to basically go through different n values and then try to select the optimal value based on the lowest mean absolute deviation. Now some characteristics, right? So if you look at the number of periods, they actually have a huge impact on how responsive your forecast is going to be. So generally speaking, right, when your number of periods is small, then that increases the responsiveness. Okay, why does it do that? It's because when the number of periods is small, then the weight assigned to each period is going to be high because you're taking a simple average, right? So as new data comes in, and if you're assigning higher weight to it, it becomes more responsive, right? Whereas if you selected a large number of time periods, then the weight assigned to each period is going to be very small. Like for example, right, if I selected 10 periods and I'm trying to forecast the demand for the 11th period, then I'm taking the average for the 10 periods, and the weight assigned to each period is only 0.1, right? So even if the demand significantly increases, right, in the next period, since a small weight is being attached to it, it's not going to be very responsive. But on the flip side, right, it has high noise dampening effects, right? So if it's just noise in the system that is increasing your demand, then it's not going to, using a large number of periods, is not going to respond to that noise, okay, which is a good thing. But it's also not going to respond to actual changes or actual increase in demand or actual decrease in demand, excuse me, right? So the idea is, right, if you use higher number of periods in a moving average model, then the forecast is going to be very flat, okay? And as you can see from some of the calculations that we did in Excel models where we compared, the forecasts are usually very, very flat, not really responding that much, whereas a small n value makes it a little bit more responsive for us. But again, in the selection of the best value for n, or the optimal value for n, you just have to go through the calculations that we have done.